right, so first question from that quiz. We had region R, this was our y-axis. Y equals e to the negative x, x equals 1, and the x-axis. And then we had region S over here, which was the infinite region extending over to the right of x equals 1 towards infinity. Does that look right to everybody? So I don't have the quiz right in front of me. I believe that's what I said. All right, no response, so I hope that's right. Okay, first thing it asked for was the perimeter. So if we're looking for the perimeter, and you're gonna have to tell me what parts B and C and D and whatever else there was were, but I know the first part was about the perimeter. So our perimeter should have been this distance plus this distance plus this distance plus this distance. So this distance should have been 1. This distance should be e to the 0, which should be 1. This distance should be e to the negative 1. And then this distance should have been your integral from 0 to 1 of the arc length formula, square root of 1 plus derivative of e to the negative x, which was negative e to the negative x squared dx. So you had 2 plus 1 over e plus this integral. And let's see, where's my calculator? There it is. That came out to be 3.561. Any questions there on part A? Okay. What was part B? Anybody offhand remember what part B was?
It's about region R, and then the cross sections perpendicular to the x-axis or semicircles. Find the
cross section. Okay, cross sections through region R or semicircles. Okay, great. So that should be the area of each cross section. So that should be 1/2 pi times the integral from 0 to 1 of the radius of this semicircle, which is half the length across the region. So that should be e to the negative x over 2 squared dx. Right, so 1/2 pi radius squared. 1/2 pi r squared for a semicircle, and then your radius is half the distance across the region. And looks like that came out to be 0.170 if you rounded it to 3 decimals. 0.1697766. And obviously, if you had not had a calculator for some reason, you could have done that integral without a calculator. Gotten some answer also, but I think everybody left it in decimal form. Good or no? Any questions there on part B? Okay. All right. And then I believe part C, I said that there is some line out here, x equals k, that divides region S into 2 regions of equal area. And I asked you to find the value of k. Does that sound right? Yeah, okay. Yeah, all right, so first thing is you need to figure out what the entire area of that is. So we want to know what the integral from 1 to infinity of e to the negative x dx is. That'll tell us what the entire area is. And that integral, if you integrate e to the negative x, what should you get? You get, first off, we'll write this as the limit as a approaches infinity of the integral from 1 to a of e to the negative x dx. But integral of e to the negative x is just negative e to the negative x. So we've got negative e to the negative x. I should probably write my limit. From 1 to a. So we've got the limit as a approaches infinity of negative e to the negative a minus negative e to the negative 1. And as a goes towards infinity, negative e to the negative a is 0. Negative e to the negative e to the negative 1 is just a positive e to the negative 1. So that's just 1 over e. And so we want half of that region. So we want half of 1 over e to equal the integral from 1 to that vertical line, k, of e to the negative x dx. And so that tells us that 1 over 2e, what this is, should be equal to negative e to the negative x, evaluated from 1 to k. Evaluating this gives you 1 over 2e equals negative e to the negative k minus a negative e to the negative 1, which becomes a plus e to the negative 1, or a plus 1 over e. So we've got 1 over 2e minus 1 over e. And any point along here now, you could have just plugged this into your calculator to solve per k, but you can also get a nice exact value too if you want to. So I had, some people did the exact value. I had written them both down on my answer key, wherever it happens to be. And so this came out to be 1 over 2e minus 2 over 2e. So that'd be negative 1 over 2e should be equal to, and then now we've got the negative e to the negative k. So that's 1 over e to the k. Sorry, negative 1 over e to the k. Negatives cancel. We just need 2e to equal e to the k. And if you take the natural log of both sides, you get k equals natural log of 2e, which would have worked, or that's natural log of 2 plus natural log of e, which is 1 plus ln 2, or whatever the decimal equivalent of that is. I believe ln 2 approximates to 0.693, so that'd be 1.693. Any of these things are fine. Any questions there on that? I think overall people did better on part A than they did on part B. I'm not sure if that's because part A was easier or because part A came first and then you ran out of time on part B, or some combination of the two. But I felt like at least number 1 was, I don't know, I felt like that was pretty doable. Let's see, number 2, I remember there was a limestone and I remember that there was a circle, but I don't happen to remember the equations of them. Anybody remember those? I think one of them was a cardioid. Let's see, I remember, I don't know, it was like this. I think one was like this, and then my circle was like right here. But I don't remember what the equations happened to have been. was it r equals 2 cosine theta and 2 plus 2 sine theta? Or did I have like 4 plus 4 sine theta and 4 cosine theta?
That's right. And also, people are putting stuff in the chat.
Oh, really? Oh, huh. Oh, that's weird. Normally, oh, okay. Normally it flashes when people put things in the chat, but it doesn't. Oh yeah, 2 plus 2 sine theta and r equals 2 cosine theta. Find the area inside the circle and outside the limestone. Cool. All right. So area outside the circle and inside the limestone. So first off, outside the circle, inside the limestone. No, inside this, yeah. Outside the limestone, inside the circle, right? Yeah, inside the circle, outside the limestone. So this region in blue that I'm sort of shading here. All right, so first off, we would note that that's just this semicircular region minus the area inside the limestone from here to here. So first thing I would do is I would just find the area of that semicircle. The area of that semicircle, this is a circle that has a radius of 1. It's got a diameter of 2. It's got a radius of 1, r equals 2 cosine theta. So the full circle should be pi units squared. So half of that circle, this semicircle, ought to be 1/2 pi. So that's the area of the semicircle. And then I'd be subtracting 1/2 of the integral of this section of my limestone. So 1/2 of 2 plus 2 sine theta squared d theta. Then we got to figure out what these values are here. So, if we plug in 0, that starts us here, but this thing's going to go from 0 around this way, right? Like if we plug in pi over 2, we should end up way up here at 4. And as we come back around, when we get to this value over here, this should be our value of pi. We should come back around here to get to 3 pi over 2 should give us 0. And so then 3 pi over 2 to 2 pi should be the limits that we're looking at here to subtract off this section right there. Everybody good with that? A lot of people had those limits off. So hopefully that's okay now. Yeah, I mean, it just so the semicircle, it's the semicircle minus the section inside the limestone is the section outside of those two. And so semicircle is just a circle with a radius, circle with a radius of 1, so that's pi units, so half of it's 1/2 pi. And then, I mean, if you just sort of trace along here, this is the value at 0. And when you plug in 0, an angle of 0, we go out 2 units. Plug in an angle of pi over 2, I should be up 4 units. I plug in an angle of pi, I should go out 2 units because sine of pi is 0. Plug in the value of 3 pi over 2, I should get -1. So it should be 2 minus 2. So I should be back at 0 at the pole here when it's 3 pi over 2. And then back over here to 2 pi. So 3 pi over 2 to 2 pi or 2 pi. Yeah, negative pi over 2 to 0 should work. That should work just fine also, Adrian. Yep. As would, 47 pi over 2 to 48, or to 47 pi over 2 to 24 pi. I mean, that would be fine too. Any of them are fine because you end up with some constants in there that end up, they end up canceling out no matter what value. Like, as long as you have the right, any 2 correct values going in the right order, it won't matter because all the big constants that you get will cancel each other out. So this would be your integral. This is a non-calculator, so you had to go through and do this by hand, which was probably the most difficult part of, I would say, the most difficult part of all of question 2. So we got 1/2 pi minus 1/2, and then you got to distribute all that out. So that's 4 plus 8 sine theta plus 4 sine squared theta d theta. So I got 1/2 pi minus, might as well get rid of that 1/2 that's there, right? So minus the integral from 3 pi over 2 to 2 pi of 2 plus 4 sine theta, and then plus 2 sine squared theta. But sine squared theta is just going to be 1/2 of 1 minus cosine 2 theta. And so the 1/2 and then the 1/2 that's going to go in front of that will cancel with the 4. So that'll just be a plus 1 minus cosine 2 theta d theta. And so now we've got 1/2 pi minus the integral from 3 pi over 2 to 2 pi of 3 plus 4 sine theta minus cosine 2 theta d theta. Everybody good with that? Okay, so now we got 1/2 pi minus, and then we'll just integrate all these 3 theta, and then minus 4 cosine theta, and then minus 1 or minus cosine 2 theta should become minus 1/2 sine 2 theta. From 3 pi over 2 to 2 pi, and 1/2 pi minus, and 6 pi minus, let's see, cosine of 2 pi is just 1, so 6 pi minus 4, sine of 4 pi is 0, so that goes away. And then minus, plug in 3 pi over 2, that's 9 pi over 2. And we got what, minus, let's see, the cosine of 3 pi over 2 is 0. And then the sine of 3 pi is 0, so that goes away. So 1/2 of pi minus 6 pi plus 4 minus negative 9 pi over 2 ought to be plus 9 pi over 2, which is going to give us 10 pi over 2, which is 5 pi, minus 6 pi is negative pi, plus a 4 is 4 minus pi. Good or no? Okay. Okay, part B, I believe, if I recall correctly, part B asks for the tangent line at 2, 0. Is that right? Or maybe it was when theta was 0. I don't remember offhand. Yeah, 2, 0. Okay. So the tangent line at 2, 0. And so we would hopefully note pretty quickly that at 2, 0, the theta value that we're looking at there is 0. Right, so we're talking about the point 2 theta, 2, 0. Theta equal to 0. And so our y value ought to be the 2 plus 2 sine theta times sine theta. So dy d theta ought to be the derivative of that, since we need to find dy dx to find the slope there. So that ought to be 2 plus 2 sine theta times cosine theta plus sine theta times 2 cosine theta. And if you evaluate that at theta equals 0, you ought to get, let's see, 2 plus 0 times 1, so 2 plus 0. So you should get 2. And then x would have been 2 plus 2 sine theta times cosine theta, and so dx d theta ought to have been 2 plus 2 sine theta times negative sine theta plus cosine theta times 2 cosine theta. And at theta equals 0, you should have then got, let's see, what would you get for that? 2 plus 2 sine theta should be 2 times the 0 ought to be 0. Okay, so 0 plus, this is 1 times 2, so 2. And so you would have got dy dx was 2 over 2, or 1. So you would have got y minus 0 equals m times x minus 2 as your tangent line. Or just y equals x minus 2. Right? Everybody good with that? And I think there was something about the area also, right? Which a fair number of people did your dy dx, got your value there, fine, or just found dy dx, but didn't plug in to get the equation somehow. I don't know if that was a time frame thing. But the rest of this one, I don't know. For some reason, I can't remember. I don't know how many people got this right, but the rest of it seemed, I thought, I was really hoping that you would see how cool this was. I mean, it's not that cool, but like you had this circle here, right? And then you had this limestone inside of it, like that. And your tangent line at this point ended up, because this point here was the point 1, negative 1, if we're talking in coordinate, like a rectangular coordinate system, it ended up just, asking you to find this little area right here, which, if you think about that, if this is 1, negative 1, and this is 0, 2, I could draw a nice little square inside of there like that. And so effectively what I'm looking at is, take the whole circle, which is pi, subtract off the area of this square, and this square, if I'm going from 1, negative 1 to 2, 0, that's 1 by 1, which should be a length of root 2 here. So pi minus 2, right? If I'm taking off the entire square, root 2 times root 2 is 2. And I had 1/4 of that. So the answer was just pi minus 2 over 4. Everybody good with that on part B? That's where I was hoping you would go with that. One, yes, Nick, you could do it with integrals, but you'd have to write the equation of this circle here in terms of, it's a circle centered at 1, 0, so you have to write it as x minus 1 squared plus y squared equals 1, and then you'd have to get the bottom half of that, which would be y equals the negative square root of 1 minus x minus 1 squared. And so that would be your circular piece, that'd be your right-hand piece of it. And then your left-hand piece of it would be the equation x minus 2. So it would have been this minus x minus 2 integrated from 1 to 2. That makes sense, Nick? To answer your question. Yeah, okay. And then, so Darius, you asked me to do it again, so I'm just gonna draw a little bit bigger. So we effectively ended up with this being the point 2, 0, and this being the point 1, negative 1, and our tangent line went through there like that. And so if we recognize this is just a circle with a, with a radius of 1, well, this is making this nice little quarter circle here. These are radii of 1 from 1 to 2 and from 0 to negative 1. And so I just said, well, we could sketch this whole thing out and just makes the arithmetic a little easier and say, this is a circle minus the square that's been inscribed within it. And then it's a quarter of that. It's just one of these 4 little regions that are identical. So I said that this is pi minus the area of this, which if this is 1 and this is 1, that's root 2. So root 2 times root 2 is 2. And since it's a fourth of that, there's 4 of those. It's pi minus 2 over 4. Does that make sense, Darius?
Yes, thank you.
Yep. All right. That's part B. Everybody good with part B? I don't know. Maybe I was asking you to do too much in too little time there. I don't know. Sure didn't think so when I made it. It seems so elegant to just like have this nice little circle with the square circumscribed, or the circle circumscribed about the square, and like it just seems so elegant. It seems so beautiful. None of you appreciated that beauty though. Oh well. All right. Then there was a part C, which I have no recollection of whatsoever. I think pretty much everybody got part C right. But I don't remember what it was. Was that one the one about the rates of change? Or was that one, there was one about a rate of change, and then there was one about the distance between the two things. Nobody remembers. Oh, there we go. There's a lot of typing there. Somebody has copy and pasted it all in here. The distance, okay, this is the one, the distance between the two curves is changing. And we're looking for the rate of change of that distance when theta is pi over 6. Okay, so if we're looking at it, talked about from 0 to pi over 2. So from 0 to pi over 2, clearly the limestone is outside of the circle, and so the distance between them is just 2 plus 2 sine theta minus 2 cosine theta. So we, I don't know, call it little d. We'll call it capital D is equal to 2 plus 2 sine theta minus 2 cosine theta, and so the rate of change of that with respect to theta ought to just be 2 cosine theta plus 2 sine theta. And then I think I just, was it pi over 6, right? So at pi over 6, that's 2 times root 3 over 2 plus 2 times a half, or just 1 plus root 3. So then part D must have been the one where I asked about the rate of change of R, I assume, with respect to time. For, I don't know, somebody's going to have to tell me what that one was too. I guess I could have just opened up this quiz on my laptop, and then I have to be going back and forth. All right. Okay, we got the particle moving along the curve. R equals 2 plus 2 sine theta. And we want to find the value of dr dt if d theta, so we got d theta dt equals 2. And so if we have r equals 2 plus 2 sine theta, then dr dt ought to be 2 cosine theta d theta dt. And we're looking for dr dt. And we said at, what did I say? Theta equals pi over 6. So this ought to be 2 cosine pi over 6 d theta dt, which ought to be 4 times root 3 over 2. So 2 root 3. Yeah, I think I would say most people got C and D correct. So, any questions there on that quiz still? Or? I'm going to assume everyone's good. All right. That should make it really easy for you to do the corrections on that to resubmit in Google Classroom, since I just did them all for you. All right. The potato problem? Up to these differential equation stuff. So we got a potato. It's been boiled. It's hot. It's left to cool. It's got a temperature of 91 degrees Celsius. That's our initial value there. And we know that its temperature is always greater than 27 degrees. The internal temperature of it is modeled by this function h that satisfies the differential equation dH dt, which is given to us there. And h is degrees Celsius. And they restated the initial condition for us again. Okay, so we want to first write an equation for the line tangent to the graph of h at t equals 0. So if t equals 0, that's the point 0, 91. And if we want a tangent line, we need a slope, and our slope should come from the derivative. So negative 1/4 of h at this point, which is 91, minus 27. 91 minus 27 ought to be 64, so this is negative 16. So your tangent line to h ought to be y minus 91 equals negative 16 times x minus 0. Or negative 16x plus 91 if you want it. However you want to write it is fine. And then to evaluate this at t equals 3, I guess we should have. We'll put a t there. So to evaluate that at t equals 3, it just gives you negative 48 plus 91, which is 43. And that was worth 3 points. 1 for getting the right slope, 1 for the equation, 1 for the approximation. Good or no? All right, part B says use the second derivative of h with respect to t to determine if this is an underestimate or an overestimate. So we want to remember that if we have a function that's concave up, the tangent line will be an under approximation. If we have a function that's concave down, our tangent line will be an over approximation on that interval, right? So we just got to find the second derivative. So the second derivative of h with respect to t ought to just be the derivative of this with respect to t. Well, if I take the derivative of it, the negative 1/4 constant out in front should stay the same. Derivative of h with respect to t is dH dt minus 0, because the derivative of 27 is 0. So we've got negative 1/4 dH dt, which if I multiply negative 1/4 by dH dt, it's positive 1/16 times h minus 27. And since our second derivative is this, no matter what h value we plug in, since h is always greater than 27, this is always greater than 0. If the second derivative is greater than 0, we know it's concave up. And if it's concave up, we know it ought to be an underestimate. Good or no? Any questions there on part B? At least Nick is answering me. Thank you, Nick. All right, and for part C, it says, okay, cool, we got now an alternate model for the temperature. dG dt is the differential equation that satisfies G. Solve this differential equation given the initial condition, and then evaluate it at t equals 3. Okay, so we'll need a new page for this probably. dg dt equals negative g minus 27 to the 2/3. Yeah. All right. And so this one, as with the majority of the differential equations questions that you will see, although only 2 of the ones that we're going to go through today, if we get to them all today, didn't actually ask you to solve them. Usually these are just questions where you solve the separable differential equation. So we'll leave the negative over here, have negative dt. Over here we'll have dg over g minus 27 to the 2/3 power. And so we'll need to integrate both sides of that. On the right-hand side, we'll get negative t plus our constant. On the left-hand side, you can do the u substitution. U equals g minus 27, and du is just dg. So really, this just is u to the negative 2/3 that we're integrating, which should go up to positive 1/3, and then we'll divide by 1/3. So that should become 3 times g minus 27 to the 1/3. Everybody good with all of that so far? Then we need to use our initial condition to solve. So our initial condition was that when t is 0, g was 91. And 91 minus 27 is 64. Cube root of 64 is 4. So we got 3 times 4. We got 12 as our constant. And then we've got 3 times g minus 27 to the 1/3 equals 12 minus t. We can divide by 3. We can cube both sides. And we'll add the 27. So g equals 27 plus 12 minus t over 3 cubed. And then it asks us to evaluate that at 3. 12 minus 3 is 9, over 3 is 3, cubed is 27, plus another 27 is 54. And that part was worth 5 points. And you'll find that whenever you have to solve a separable differential equation, that will be worth somewhere between 4 and 6 points. It's always like the heaviest weighted part of the question. So 1 point for just separating the variables, 1 point for the correct antiderivatives, 1 point for having a plus c and solving correctly for it, 1 point for finishing solving to get the equation, and 1 point for your approximation, or not your approximation, but your value of g of 3. Any questions there on the potato? Fun, yes. Boiling potatoes is fun. To make all kinds of wonderful things. Is anybody still here besides Nick? Is Nick the only one that's still alive? Did I kill the rest of you with boredom? Cool. All right, let's look at this one. dy dx equals x squared minus 1/2 y. So if you took AB last year with me, you'll find that most of the differential equations last year just required you to solve the differential equation with like a couple other small little pieces to it. But oftentimes on BC, more often on BC, you don't actually have to solve the differential equation. That doesn't mean that you won't have to. There are plenty where you do. But sometimes you don't have to, you just have to do a bunch of other junk with it. So this is a good one to sort of practice some of that other junk that you need to be able to do with it. So first off, finding the second derivative. So our second derivative, derivative of x squared is 2x. Derivative of 1/2 y is 1/2 dy dx. And if you leave it in this term form, like 1/2 dy dx, they will not give you the points for that. You need to do 2x minus 1/2 of x squared minus 1/2 y. You need to resub your dy dx in there. And it'd be nice to get 2x minus 1/2 x squared plus 1/4 y even, but you don't have to simplify it. Everybody good there with part A? That was worth 2 points. 0 points if you did not substitute out the dy dx though. So make sure you do that. All right, part B, we got y equals f of x is the particular solution to this differential equation. It passes through -2, 8. We want to know, does f have a relative min, max, or neither at -2, 8? So the first thing we'll need to do is we need to see if the derivative equals 0 at the point -2, 8. Because if the derivative isn't 0, then you don't have a critical value and you can't have a min or a max. So it would be neither. So at -2 for x, that's going to be 4. And then minus 1/2 of 8 is also 4. So it could have a max or a min. And the only way for us to determine this, since we don't know on our actual function as x, suppose we went to like x equals -1, we don't know what y equals for that. So we can make a sign chart for this. But what we can do is we can go in and plug this value into our second derivative and use the second derivative test, right? So if the second derivative tells you that at a critical value where the derivative is 0, if the second derivative is positive, it tells you you're concave up, which means it's going to be a min. If the second derivative is negative, it's going to be concave down, which tells you that that critical value is a max. So we'll plug in -2 for x. So that's going to be 2 times -2 is -4. And then minus 1/2 x squared. So that's going to be minus our 4 times 1/2, so -2. And then 8 is going to give us plus another 2. And that gives us -4. -4 is less than 0. Tells us it's concave down on that at that point. And it tells us that it is a maximum because the function is concave down. And the fact that it's a max with an explanation, just this is good enough as your explanation that the second derivative value is negative. If you want to be more specific, say the second derivative is negative, meaning the function is concave down at that point, meaning that the critical value must be a max. That's worth 2 points. Good or no? Still Nick. Nick is the only one that is still good. Oh. Ashley is still alive. Darius is still alive. Some of you are still awake and alive. That's great. Ooh, Adrian is good with a capital G. My goodness. Even better than the rest of you. All right. So part C gave us g of x, which is a particular solution to the given differential equation with g of -1 equal to 2. Oh, wow. Gold. Yes, exactly, Nick. Gold. Okay. Yeah. So then we're going to find this limit. So we have this new initial condition. Yeah. Yes. I got that it had 2 capitals, Nick. That was gold. Yes, I'm pronouncing it differently because of the giant go. Go odd? Yes, I don't know. All right. I tire of the nonsense I've created. So we're looking for this limit. So this is going to be g of -1 So let's write this out. Limit as x approaches -1 of g of 1 minus 2 over, what was it, 3 times x plus 1 squared, I think. Yeah. And so since we know that g of -1, sorry, -1, since we know that g of -1 is 2, this is 0 over 0, which means we can use L'Hopital's rule. I guess I should have written g of x there. So that's going to give us then the limit as x approaches -1 using L'Hopital's rule of g prime of x minus 0 over, and then the denominator's derivative ought to be 6 times x plus 1. And if we were to plug in g prime of -1, let's see here. Oh, right. We have a derivative up here. Ha. G prime of -1 we should be able to figure out. We just need to evaluate dy dx at -1, 2. I was thinking. X squared, so -1 squared is 1, minus 1/2 of 1. Looks like that's still 0. This is still 0, so we'll take another derivative. Using L'Hopital's rule again, we've now got the limit as x approaches -1 of g double prime of x over 6. And now we'll just use our second derivative at the point -1, 2. And let's see, our second derivative. Let's see, the first number got to be -2 there. Then plug in -1 here, that's -1/2. And then plus 2, so -1/2 plus 2. So that ought to be -1/2 for g double prime of x. Over 6. Did I do that right? -1. Oh, that's a -2. Oh, that's plus 1/2. I know how to multiply. That's -2. Yeah, you got to multiply it right though. -2 over 6, which is -1/3. Good or no? I wrote a 1 there. That should be a 2. Yeah, you're right, Megan. That should be a 2 there. 1 minus 1 is 0. I think I just wrote the 1 because I started evaluating it in my head already or something. Which I believe is the same thing I did over here. So we get -1/3. Everybody good there with part C? All right, and then part D. On part D, we're going to use Euler's method, starting at x equals 0, 2 steps of equal size to approximate the value of h of 1. So we've got h of 0 equals 1, and we want h of 1. And we're going to to start at 0, and we're going to use 2 steps. So 1 to 1.5, 1.5 to 2. And what was our derivative to begin with? dy dx was x squared minus 1/2 y. Is that right? Yeah. Okay, so our original point is 0, 1. And we're going to have to, h of 0 equals 2. Really? Oh, okay. I just looked at it and then I wrote the wrong thing. I did. Wow. Did the same thing I did a minute ago. I wrote the 1 because I looked at that next one. I gotta slow down here. All right, h of 0 equals 2. There we go. So our first value for dy dx should be when x is 0, y is 2. So that should be dy dx equals -1. Okay, just making sure I did my arithmetic there correctly. So as x goes up by a half a unit there, our y value ought to go down by -1. So our new point should be becoming 1/2, 1. Sorry, 1/2. This is not 1/2, 1. I didn't multiply. Since our delta x equals 1/2, our delta y should be -1/2. And so our new point should be 1/2, 3/2, right? Going from 2 down 1/2 to 3/2. So we got 1/2, 3/2. And then our new dy dx, when we plug in 1/2 for x, ought to be 1/4 minus 1/2 of 3/2, which should be 1/4 minus 3/4, should be -2/4 or -1/2. And since our delta x is 1/2, our delta y ought to be -1/4. And so delta x of 1/2 gives us 1, and 3/2 minus 1/4, that's 6/4 minus 1/4, ought to be 5/4. So your point ought to be 1, 5/4. So h of 1 equals 5/4. Got it or no? We all have vague recollection of how to do Euler's method. It's been a while. Part C, again, there's part C. Somebody asked for part C again. Oh, I didn't really give you guys the point breakdowns on this one, did I? Let's see here, part C. If you just use L'Hopital's rule, you got 2 points. And then if you got the final answer correct, you got another point. And then for the last one, if they could see you were using Euler's method, you got a point. And if you got the right answer, you got a point. All right, everybody good with all of the parts of that? All right, I don't think we have time to do this one right now. So hopefully you've done this one and this one already. And for tomorrow, I guess let's do the baby bird problem. That's a good one. The baby bird and the trash. That's, those are the same basically. I don't know, do these next 3. Do the baby bird, do the trash, Nah, I don't know. Don't bother with the trash one. It's like exactly the same as the baby bird. Actually, never mind. Do the baby bird, do the trash, and do these next two. That'll be good. So do pages 5, 6, 7, and 8. Baby bird, trash, 7 and 8. Yeah, 8's a good one. It's got a Taylor polynomial thing in it, and both of those will be good. And I won't go all the way through the baby bird and the trash problem because they're almost identical and they're just like the potato problem. But if you have questions on them, I'll help you out with them. So pages 5, 6, 7, and 8. And those are all that I will assign for the differential equation stuff. You're welcome to do any more than that as practice for the quiz on Thursday.